Okay, sorry about that. We had some technical difficulties in the classroom. So anyway, I think we were talking about the algorithmy here, which is a way of doing things, an algorithm is. And the interesting thing that we hear from Al-Khwarizmi is that we only need 0 with some advanced thoughts. So with 0 and some advanced thoughts, we can start to see things like calculus concepts developed. In his book, Algorithmy, he actually focused on 2 major things that we see. One is the method called Al-Jabr, J-A-B-R, Al-Jabr. So there was that method. And often he would call it the method of restoration. So we've got an Arabic name for it, and then we call it the method of restoration. And basically what this becomes for us is a very basic algebraic rule that says I'm allowed to add equal terms to both sides of an equation. Now, to us, again, in modern days with modern algebra, that sounds like, yeah, of course we can. But in that day, this is kind of a groundbreaking idea that an equation is something that is basically a balance. And so, therefore, I'm allowed to add to one side of my balance as long as I keep it balanced on both sides. So I can add to the other side the same or an equivalent amount or quantity. Okay, so there's that guy. And then there's this guy, A-L-M-U-Q-A-B-A-L-A method. I call it Al-Muqabala, the Al-Muqabala method. And this one, if this one up here is restoration, then this one down here is often called the method of reduction. Okay, so think about that. If restoration was adding and then we want to reduce, then the reduction method would be, hopefully you guessed it, yep, I can subtract equal amounts or terms or quantities, however you want to think about that. Equal quantities, I'm going to say, from both sides of an equation. In order to reduce something. Okay, so for us, this is very basic algebra. Let's say I have something like 3x plus 7 equals 8 minus x. If I wanted to get my like terms on the same side of the equation, for instance, I can add an x to both terms. The process of doing that for purposes of Al-Khwarizmi, that process or that method is Al-Jabr. Okay, that's what just happened there. So then we would have something like 4x plus 7 equals 8. And what's the next step in our process to solve this thing for x? Of course, I would subtract 7. So the process of subtracting that same exact quantity from both sides, this becomes what will be known as Al-Muqabala, or the method of reduction. So now I have something that looks like 4x equals 1, and then I'm out of space, so we're just going to say, then later we'll develop this process that says, okay, I can divide both sides by the same quantity, or I can multiply it by the same quantity. We know that those are opposite operations, multiplication and division, just like adding and subtracting are opposite operations up here. And so we would be able to solve that particular equation for x, of course. So I've said multiple times now, I've said Al-Jabr. And multiple times I've said in our study of what is currently known as algebra. Al-Jabr, algebra. Al-Jabr, algebra. It is not a coincidence at all. So what happens is Al-Jabr which is this process of adding the same quantity to both sides, becomes translated into, from the Arabic into the English, and we would call it algebra. Very, very similar words. It's something that's transferred over from their language to ours, and so we see it in there. All right, so that's the kind of stuff that he was working on from the algebraic standpoint. He also developed a very clear form of completing the square. So I'm going to move this out of my way. He spent a lot of time working on this, and if I were a betting person, I would bet that you will see a complete the square problem on your first exam, which is in a couple of weeks. And you'll need to know that this came from Al-Khwarizmi and how it works. So let's get us a very clear example. He was doing things like x squared plus 10x equals 39. So modern day we have a process called completing the square where, for instance, we have to get all the x's on one side and all the whole numbers on the other, or whatever other numbers there are on the other side. And the coefficient for the x squared term here needs to be a 1. That's already done for us here, and the situations that he's going to address in his books are going to be very similar to these. So that first little bit of completing the square is already going to be done for us. Okay, but he's going to take the very literal square part of this and tie in geometry and tie that in with the algebra. And as far as I know, he's the first one who actually did this and put a process to it. So again, just like as the Egyptians did it, when they're talking about x squared, they're talking about, for instance, a square piece of property or a square piece of paper or something like that. It's x times x. That's what they literally mean by x squared. Okay. Whenever I'm doing, for instance, here, I've got this x squared plus 10x. One of the things that they might do is they might take that 10x, and if you've ever done any work with algebra tiles or algebra blocks, you might have seen something like this. If I had just one piece here that was x units long and 1 unit wide, that would be the rectangle whose area is 1 times x, right? Because length times width, 1x, just like this square is, his area is x times x, or x squared, right? Let me do that so we can mark it. Okay, so what he would do, he was working on doing is, hey, maybe I can take this particular quantity, 10 x's, and maybe I can split it up amongst the different sides here. Okay. So if I did that and I took all of the x's that I have, which is 10 of them, and I split it up amongst the different sides that I have here, which is 4 of them, then each of these pieces would be 10 over 4 units wide. I guess I should put that down here. 10 over 4 units wide, and each of them would be x units long. Okay, so whenever he starts working on this, he's like, hey, what in the world can I do with this? And he figures out pretty quickly that one of the things he can do, instead of splitting it up 4 ways here, because then I'm going to have to fill in all 4 of these little boxes, right, and figure out how big those are. Instead of doing that way, maybe I can do it this way and take that x squared guy. So here's my x by x. Take the 10 x's, and instead of making it this way off of all 4 sides, maybe I can just split it in half. Okay, so what's half of 10? And of course, the numbers that I'm going to give you are normally going to be nice numbers here. So here I would add a rectangle here that's 5 units wide and x units long. So that would be 5 times x. So his area would be 5x, which is half of this guy. And then I would do the same thing here. So here would be x, this would be 5 units long. So what I've got here is, right here on this portion, I've got 5 x's. And on this portion, I've got 5 x's. So if I have x squared here, done, and I have 5x here and 5x here, I've split up those 10x, but it's still a total of 10x, so done, okay? And if I want to literally complete the square, I need to fill in this piece right here and see how big that box is going to be, okay? How big is that portion? It's going to be a square, actually, that I'm filling in to make this a total of x plus 5 times x plus 5, so that I still have a square there, okay? It's just that instead of x times x, now its total length is x plus 5 and x plus 5. So how can I do that? What is the number that I'm filling in here? Well, to do that, what we have to do is figure out how wide is this little square and how deep is this square, or how long. So we know it's 5 wide up here, so this is 5. And we know it's 5 tall here, so that's 5. So this square that I'm missing that I need to fill in is the square that's 5 by 5. 5 squared is 25, right? Okay, so, and we'll talk about this whole process, but what's going to happen here is that this fill-in square is going to be 25. All right, so what Al-Khwarizmi came up with was, hey, I can complete this square. I can add this 25, because that's what that is. So now I've got x squared plus 10x plus, and we figured out what that number is that I'm adding, which is 25. Added it on the left-hand side of the equation. And if I do that by the method of algebra, whatever I do on the left-hand side, I've got to do on the right-hand side. So I added 25. I need to also add 25 over here, right? All right. So by doing that, I'm like, hey, okay, now I see I've got a really good thing going on here. Interestingly speaking, whenever I look at this, this is now turned the left-hand side. In modern day algebra, we would say the left-hand side is now a perfect square trinomial. So this becomes x plus 5 times x plus 5. On the right-hand side, I'm just going to add those two things together. It should be 64. Okay, this is a binomial squared. X plus 5 times itself is x plus 5 squared. So I've got x plus 5 squared equals 64. And then in order to solve that, of course, we all know I need to get rid of this square. So the undoing operation for squaring, or the opposite operation, is square rooting. So whenever I do that, I'm going to take the square root of 64. So I get x plus 5 equals, the square root of 64 is 8. Now for our purposes, we are only using the positive, and that's because we're dealing with a geometric shape that I'm looking at its area, right? So I'm trying to fill in the dimensions and stuff. So all of those are going to be positives. I would not have a negative, a side length that's a negative 8, right? Okay, and then I'm almost done. All I need to do is subtract 5 and use my al-Muqabala. That guy goes away. And I've got x equals 3. Okay, so we have a solution for this particular problem, which is amazing. And what we see here is a couple of things going on. And the big one for us is that this opens up the door really wide for quadratics, right? Quadratic equations, coming up with the quadratic formula. In fact, the quadratic formula can be directly derived from completing the square. So we'll see a lot of advances that come along dealing with polynomials of higher degrees, and a lot of it comes back to this work right here. Okay, so I want to go back and just fill in for just a second for those of us who maybe don't remember how to complete the square, like algebraically speaking. There are some steps. So number one, like I said, x is on one side, numbers on the other. That's already going to be done for you in most of these cases. Number two is 1x squared. We need to make sure that that coefficient is a 1. If it's not, then we're just going to divide by whatever's there, or if it's a fraction, we'll multiply whatever's in that fraction by its reciprocal. But this is where we're going to normally start for our purposes. So number 3, what we do is, if you'll remember, this is my A guy, and this is my B guy. Let me write it here. Here's my A, here's my B, and we're trying to figure out the C is what we're trying to do in a traditional quadratic equation. Okay, so the A is going to be a 1 because that's part of the completing the square process. So all I need to focus in on is the B because I'm trying to find the C. We don't have him yet, right? So I'm focusing on the B. So what did we do? We had a 10 and we split it in half, right? 5 of them down here, 5 of them over here. So you take whatever your B term is, your coefficient, and divide it by 2. Split it in half. And then that 5, we did 5 times 5, right? So we squared it, multiplied it by itself, basically. So B over 2 squared. And what did we do with it? Well, right here, we added to both sides, right? Okay, so that's the algebraic step. If you don't remember this, maybe go watch a video on completing the square or something like that. I'm going to give you a couple of problems to work on, but that's the process. You add that number to both sides. And if we did it correctly, step 4 is we get a binomial squared. Okay, so that's what happened right here. I had x plus 5 times x plus 5. It was x plus 5 squared, so I got my binomial squared. I write it as a binomial squared because I want it to look like this so that I can apply the square root property. Okay, so if you remember this and it's all good, no worries. But the last step there is solve for your variable. In this case, it's x. And in most cases, people will just take the square root of both sides, and then if they need to add or subtract from both sides of the equations, they'll use their algebra or their al-mukabala. Yay! All right, so that's the process. For our purposes, you need to know both. So you need to understand what's happening over here as far as the algebraic step, and you need to be able to fill in a nice pretty square there and tell me exactly what's going on in the squaring portion of that. So if you would like to practice your skills, if you're not sure that you know exactly how to do completing the square, I've got a problem here, x squared plus 8x, uh-oh, I ran my finger through the red ink. X squared plus 8x equals 9. You can try that guy. If you want some more advanced guys, this is the type that probably he was working with, but if you want some more advanced, like more modernized ones, here's one. X squared plus 20x minus 32 equals 0. You would need to get the number by itself, basically. I've got a fun one for you. X squared plus 5x minus 12 equals 0. And why is that fun, you might ask me? Well, the answer is because my b is an odd number there. So if it's an odd number and I go to divide it by 2, it's not going to go in evenly. So what about that? Oh, now I'm going to have a fraction, right? So we're going to have to mess with a fraction. And then one more, 3x squared plus 12x minus 27 equals 0. All right, so here's some practice problems. You're not turning them in or anything like that, so if you don't want to do them, you don't have to do them. But if you feel like, oh my gosh, it's been a while since I've done completing the square, and you want to look at that, then go for it. So these should all have, well, except for the 5, because of course that one's odd, but they should all have some pretty nice round answers to them. The 5 is going to be 5 halves, and then you're going to square it, so that's not quite so nice. All right, but that's a little bit of practice for you. All right, so what happened from this? Kind of cool. Al-Khwarizmi began generalizing to all types of problems. Okay, so what do I mean by that? The types of problems. This is actually something you've probably seen like in a discrete math or something to that effect, where they'll say, oh, case 1, case 2, case 3. So for instance, if I was looking at these problems I just gave you, this would be the type of problem where I've already moved the C term, because it's not quite C to the other side. This would be the type of problem where I haven't moved it. This would be the type of problem where I've got an odd coefficient for B. This would be the type of problem where I still have a coefficient other than 1 out in front of the x squared. So he's starting to generalize things and solving quadratics. So in order to solve the quadratic, what we see is that Al-Khwarizmi is sometimes going away from the geometry. So he starts by developing the geometry and then creates the algebra that goes with it. But what happens, this generalizing thing, he goes away from the geometry, and sometimes getting away from the Greek method only does algebra. Okay. So in modern mathematics, sometimes we link our algebra and our geometry together. We may have graphs of things and then talk about the algebraic equation that goes along with that graph or something like that. But for our purposes here with Al-Khwarizmi, it's maybe a departure from the norm to be able to just work with the algebra and to leave the geometry behind. Later on, what we'll see is he's writing in Arabic, but later it'll go into Latin, which becomes like the language of the scholars, basically, right? Okay. So he writes a book. It's called Liber Al-Khwarizmi when you convert it or translate it to Latin. Okay, so his was Algorithmi, but whenever we translate it into Latin, it becomes Liber, which means book, and Algorithmi. Okay, he also had a book called A Book on the Form of the Earth. Okay, and this was where he was working with lines of longitude and latitude and stuff like that. So that guy's out there. Book on the Form of the Earth. What else did he do? This book on the form of the earth actually listed locations, like different places using their latitude and longitude. So maybe we could talk about this is the very, very earth, beginnings of GPS or Google Earth or something like that, okay? And something interesting, he was part of a team that was trying to measure 1 degree of the meridian. Like, how far is that, is what he was trying to measure. And what he came up with, they came up with 56 2/3 miles. Okay. Now, that's not accurate. I believe the answer is more along the lines of 20,000 miles. Okay. But he was doing some math and trying to measure weird things like what's a 1 degree of the meridian. So that's kind of fun. He wrote a book called, that when it was translated, was called Liber Quadrans, which basically means the Book of Squares. So think, he's writing in Arabic, it's getting translated to Latin, and now we're looking at it, okay? Some interesting stuff that happened in there was he was dealing with x squares. He was dealing with the Pythagorean theorem, which, as we know, has been around for hundreds of years now, probably thousands, okay? And he dealt with, in particular, Pythagorean triples. So things like, if I have a right triangle, I can have a 3, 4, 5 right triangle. And the big thing that the big thing that he's delivering for us is notation, notation, notation. So we can thank him for sure for coming up with exactly what we want our, exactly what we're wanting our x squares to look like and things like that. All right, so I believe I'm about out of time whenever I add the 2 videos together. We have one more guy who's an Arab that we really want to get to. So his name is Omar Khayyam. If you're reading in your book, you should go ahead and finish out that section on Arabs and I will pick him up next week, or the next class period. So just be aware that one more Arab guy is out there before we start moving on even farther. And we are getting really close to being more modernized math, which is just about perfect because test 1 is coming up soon, right? So it's going to work out for us. All right. Have a good evening. Thank you.